Hi class. So this is going to be a lecture on friction, which is going to be 5.1 in your book. And there's going to be two types, static and kinetic. And they're both basically the same equation. So static is, and they're both going to be lowercase f is how we're going to denote the forces. So static is going to be mu s times the normal force. And then N is the normal force. So I can go ahead and write that there. And so that's something that we learned in the Unit 2 with the forces. And then kinetic is basically going to be the same equation. And we're just going to denote it with K. So really the same equation for both of these. And we can also leave the subscript out sometimes when we're only using one of these. But some of the problems in the real world, there's going to be two different types. So static means it's still, kinetic means it's moving. And you can kind of think about it, say you're pushing something on the ground, like a box or anything like that, and it takes more force, oftentimes, to get started than it does once you actually get it moving. And that has to do with on the microscopic level of the roughness of the surfaces. And to tell you the truth, this is more of an approximation that we use for these introductory physics courses. When you do this in the real world, usually it's more like air resistance, which is proportional to velocity, or other orders of the velocity, and it's usually, in this case too, determined by experimentation. So this problem we're going to do, which is the example in your book, is one where we actually find the coefficient. So yeah, these are the only two equations that you really need to know for this type of friction. And so go ahead and go over this problem in the book. It also has a little bit of trigonometry. It's an inclined plane problem that we don't do as much in this course as you'll see in some courses. But so yeah, I'll go ahead and erase this stuff here. Erase that S. And so we'll just use that equation for friction and draw this inclined plane here. Plane problem with the skier. So there we go. Here's the inclined plane. I'll go ahead and draw the axis here real quick. Just it's helpful. So this is Y and X. And we don't necessarily use the Y and X in this, but it helps that it kind of helps us. And we can also kind of tilt this axis is kind of what we'll do. But I won't go into that. Hopefully it won't be as confusing. So this angle here is going to be theta. That equals 25 degrees. And then you'll have a skier here. Do the skier in purple. Oh. Okay, and then I'll go ahead and do the forces in black as well. So you always want to draw the forces when you're doing this. And we have the force of weight, which is going to be mg, and it's denoted by W in your book. And then we have the normal force right there. And so that's always going to be perpendicular to the surface. So as you can see, the weight and the normal force are not lined up right now. And so we'll have to define what the weight is perpendicular to the surface. And that'll be, we'll have to use trigonometry to find that component. And then we're going to have friction 2, which is the friction force there. So that's always going to be perpendicular to the surface. And so that F is going to equal mu times the normal force. So basically what we're going to need to do is break this weight up into components like this. So I'm doing this in a different color because we're breaking this force up into different components. And so using trigonometry, you can kind of see this 25 degrees here, because it's a right triangle. You can kind of see if we extended that down there, we'd make a triangle there. It would be kind of like, I'll just draw this real quick. Let's see, we'd have a triangle like that. So that'd be 25 there. And that'd be 90 minus 25, which would be 65. And we'd have another right triangle there. And since this is a right angle, basically that angle is going to be 90 minus 65, which is 25. So using trigonometry, you can figure out that, and I'll erase all this stuff here. You can figure out that this angle here is also 25 degrees. That's also 25 degrees. So I'm not going to do a whole lesson on trigonometry. Hopefully you followed how I figured out what that angle is, but that is going to be a certain part of this problem. So what we want to do is, since we know that angle there, we need to find this component, and that'll be the equal to the normal force. So cosine is adjacent over hypotenuse, and this is going to be the adjacent angle. You can kind of see we have a triangle there, and so I just moved that other force up to the top, but that's basically the triangle. And so we have a adjacent angle there, and so that's going to be cosine. So we can write these equations out. Now we know that the normal force is going to equal the weight, and that's the whole weight times cosine theta. That's 25 degrees. So that's going to be mg cosine 25 degrees. So I don't think we have the weight of the skier, but we can figure out the friction. Maybe we do have the weight of the skier. But nevertheless, we can still figure this out. And so the friction force is just going to be mu times n. So that's going to be, oh yeah. So we know, let's see. So we know mu times n is going to be mu times that. So that's mg cosine 25 degrees. Yeah. So we know we don't know mu, we know the force of friction, and we also know the mass. So just doing some algebra there, we can move that. So mu is going to be equal to F divided by mg cosine 25 degrees. And that's the answer to the problem. It's going to be lesson 1, and you just plug that into your calculator, and hopefully that going through that problem helped you solve these. I know it's in the book, and referring to your book is always what you're going to want to do, but going through the examples I think sometimes helps. All right, well, thank you very much.